First, I'm going to give you the definition of independence. So, definition. Two events, A and B, are called independent if the following holds true. The probability of B given A is equal to the probability of B. So that's the definition of independence, and I just want to explain why this makes sense. We obviously have some sense, some idea of what independent means in our everyday lives. Independence means no relationship. It means that one thing is free to move independently of the other. So if A and B are independent, then what that means is that these events have no influence on one another. In other words, it should be true, if A and B are independent, it should be true that the occurrence or non-occurrence of event A has no influence on the probability of the other event, B. Okay, the probability of B occurring should be unaffected by the occurrence or non-occurrence of A. And that's exactly what this equation actually says. If we remember from yesterday what this notation means, it says this is the probability that B occurs given the fact that A has already occurred. Okay, that's what the left-hand side is. And the right-hand side is just the probability that B occurs without the assumption that A has occurred. So this guy, the left-hand side, is the probability of B happening given that A has occurred, and this is the probability that B occurs without making the assumption that A has occurred. And the fact that these two things are equal is telling you that the probability of B remains unchanged if you assume that A has already occurred. In other words, the assumption that A has occurred has no influence on the probability of B occurring. So that's why it makes sense that this is the definition of independence. Okay, so that's the definition of independence. I think I would like to do an example. Let me just pull up my worksheet. I want to remember exactly what my example is here. Just 1 second, bear with me. Okay. Yeah, so actually what I want to talk about now is the test for independence. Okay, so if you very often what we do with independence is we'll ask you, whether two events are independent or not. I'll give you like two events, and I'll be like, okay, are these guys independent or not? All you have to do is check this formula. Just verify if this equation is true. It turns out, though, that sometimes the left-hand side of this thing is kind of annoying to compute. What I'm going to do is derive an alternative equation that can be used to check whether two events are independent, that most of the time is easier to work with than this version of the formula. So to do that, let's just recall from last time. I gave you the formula: probability of A and B is equal to the probability of A times the probability of B given A. So that's the probability that A and then B occurs, right? That's what this thing is, the probability that A happens and then B happens. And that's equal to the probability that A occurs times the probability that B occurs given that A has already occurred. You might remember that from last time. Well, the thing is, if A and B are independent, okay, if they're independent, that means that this formula in the box holds true. So if A and B are independent, that means that this expression right here, the P of B given A, is actually equal to just P of B. That's what this equation says, right? If they're independent, then P of B given A is the same thing as just P of B. So if A and B are independent, I can replace this term here with plain old P of B. So that's what I'll do. And I obtain this. Okay. This is an alternative formula for determining whether two events are independent or not. This is often called the test for independence. So very often, if I give you two events and I say, are they independent or not, it is in fact easiest to look at this formula. You compute the left-hand side probability of A and B, you compute probability of A, you compute probability of B, You plug in all the numbers and you just see whether or not the equation holds true. If it does hold true, the events are independent, and if it doesn't hold true, then they are not independent. Although really, you can use either one of these formulas. I mean, they get at the same information, so whichever one you want to use is perfectly fine, although I think most of the time this one's better. All right, so that's all pretty abstract. Let's do an example. So what I'm going to do is I'm going to construct a table, and we're going to imagine that there are a bunch of students, okay, maybe in a class or something, or in a school, and each student studies exactly one language and exactly one science. And I'm going to make a table that just sort of catalogs how many students study each subject. So I'm going to have some rows, so French, Spanish. I'm going to represent French with F and Spanish with S. And then I'm going to have some columns in which I'm going to place the sciences. So let's say chemistry, C, physics, P, and biology, B. All right. And I also want some totals. So like I'm going to have a row for the totals, and I'm going to have a column for the totals. And I'm just going to populate this table with some numbers. So going across, I have 7, 4, 3, 14, 1, 6, 9, 16, 8, 10, 12, and 30. And I'm just going to ask some questions about this table. So let's start with a simple one. Suppose you choose, so here's the setup. You choose a random student. Okay, so you just choose a random student. Find the probability of F. That is, find the probability that they study French. Okay, well, let's think. So we're choosing a random student. How many total students are there? In total, there are 30. That's the grand total, right? So we're choosing from a pool of 30 students. And of those, how many total study French? Well, that would be 14. Okay, cool. How about the probability that the student studies French given the fact that they study chemistry? Now, how does this given chemistry thing change our answer here? Well, what we're doing now is we are assuming that they study chemistry. We are restricting our attention only to the students who study chemistry. Okay, so we're no longer actually choosing from the entire group of 30 people, but rather we're just choosing from the people who study chemistry, of which there are only 8 people. So we're only choosing from a pool of 8 people. And what's the probability that we're choosing one of those random people? Out of those 8, how many of them study French? That would be 7, right? So the probability that someone studies French, assuming, given that they study chemistry, is 7/8. Now, here's a question. Are the events F and C independent? Okay, so the two events are student studies French and student studies chemistry. Are those events independent? You can tell right away that they're not, because these two things aren't equal. All right, this fraction reduces to 7 out of 15. Okay, so that's reduced, and so is this fraction. To compare fractions, you really have to reduce them. These two fractions are not equal. Okay, if you go back to the definition of independence, it says that, the probability of B happening given that A has occurred should be the same as the probability of just B happening without that assumption. In our case, that translates to, if the events student studies French and student studies chemistry, if those events are independent, then making the assumption that they study chemistry should have no influence on the probability that they study French. In other words, making this assumption here, restricting our attention to the students who study chemistry, we should find the probability that they study French is the same as without that assumption, which is what we had here. But as you can see, they're not, right? They're two different numbers. Assuming that the student studied chemistry, restricting our attention to the students who studied chemistry, changed the probability that the student studies French. That means that the event C, its occurrence is having an influence on the probability of F occurring. So they are not independent. So the answer is no. Now let's try and answer the same question again So here what I did was I appealed to the definition of independence. But, as I said, I gave you this other formula, which is an alternative formula for testing independence. We usually call that the test for independence. We could have used this formula as well, okay, to answer that question. And in fact, let's do it that way. So the test for independence says the events f and c will be independent if and only if the probability of f and c is equal to the probability of f times the probability of c. So the question is, are those two things equal? If they are equal, then they're independent, and if they're not equal, then they are not. Okay, what's the probability that they study French and chemistry? So, we're picking from the entire pool of people here. We don't have any given probability, right? We're not assuming anything, so we are drawing from the entire pool of 30 people. So probability of French and chemistry, we're pulling from 30 people, and how many of them study both French and chemistry? That would be 7, right? So 7 out of 30. And the question is that equal to the right-hand side? Well, probability that they study French, again, we're choosing out of 30. How many of them study French? 14. So 14 times, and then probability that they study chemistry, again, we're pulling out of 30. How many of them study chemistry? Looks like 8, right? Okay, so are these two things equal? They certainly don't look equal, and so you might be tempted to just say, no, they're not equal. In fact, we already know that they're not equal because we already determined that these two things aren't independent. But still, I just want to caution you, when you're doing this test, sometimes it looks like the two sides aren't equal, but to be really sure, you have to reduce and simplify all the fractions and then compare them. Like, the only way to be sure that two fractions aren't equal is to reduce them completely and then see if they're the same. So sometimes they'll look very different, but they actually wind up being the same. So the left-hand side's already reduced, right? 7 out of 30. The right-hand side, though, can be reduced. The right-hand side is actually, okay, so 14 out of 30, we can divide top and bottom by 2. That gives me 7 out of 15. And here, 8 out of 30, I can divide top and bottom by 2 as well, so that's 4 out of 15. Okay, so that's going to be 28 out of 225. There are no common factors between 28 and 225. I mean, you can see that there's no common factors, right? The only things that, only 7 goes into 7, only 2 goes into 4, and neither of those numbers go into 15. So this is reduced, and this reduced number is not equal to 7 out of 30. So no, these two equations are not, or these two expressions are not equal to each other. Therefore, the events are not independent, which we already knew. Yeah, so, just a quick summary here. What we've done is we've defined independence, and, we've sort of given you the definition and then a test. And really, you can use either one of these formulas to determine whether or not two events are independent or not. And, the idea is that if two events are not independent, that means that perhaps there's some relationship between them. I do want to caution you, though, when we ask you a question like, are these two events independent? We want you to just do the formula and check to see if the two numbers are the same. That's what